All right, welcome to lecture 16. And today's topic is, oh, hang on, there we are. Today's topic is triangulation and trilateration, kind of a sequel to our discussion on radiometric navigation. So last lecture, we spoke quite a bit about methods of radiometric navigation. We talked about the way that we use radar and radio measurements from space to estimate the position of a spacecraft. But we kind of talked about it in a hand-wavy, lot of words, not a lot of math kind of way. And today is going to be the complement to that, where it's not a lot of words, it's a lot of math. It's going to be very helpful for homework 3. So we talked about the two main radiometric navigation kind of, we would call them examples, basically, which are GPS and the Deep Space Network. So GPS is using satellites to help you navigate on Earth. Deep Space Network is using Earth-based measurements to help you navigate in interplanetary space. Or, you could be closer. You could use DSN for lunar navigation as well. We talked about time of flight, time of arrival, time difference of arrival, VLBI as methods of getting range. Essentially, we get range, range rate, and bearing are the three main types of measurements that we can get from radio waves. GPS uses exclusively range measurements, but they aren't really range measurements. They're pseudo-range measurements. And we talked about that a little bit towards the end of last lecture. But basically, if you know the distance that you are away from 3, or in this case, 4 spacecraft, that gives you enough information to uniquely determine your position. And today we will talk about exactly how we do that. Deep Space Network, we talked about kind of the global coverage of space that we achieve with 3 stations in Goldstone, California, Madrid, Spain, and Canberra, Australia. We talked about one-way, two-way, and three-way radiometric ranging. We did a quick kind of warm-up problem where I wanted to see if we could go from this measurement model to a linear system of equations that we solve for the range, or the position, I should say, of the observer. And then we set up a little bit more accurate form of the problem, and we landed on, after quite a bit of math, we landed on this equation right here. So I'm going to put a little star next to it. So this is not the range, it's the pseudo range. So it's going to be noisy. It has a bias in there, and it also has multiple biases. It has the bias of the receiver camera, which we can't ignore. It has the bias of the transmitter camera, which we can account for. It's typically calibrated. And then it also has ionospheric delay, interplanetary, what is it? Interplanetary medium delay, ionospheric delay, and tropospheric delay. So the speed of light in a vacuum is a constant, which is, fantastic, but it's not a constant when it's traveling through the atmosphere, or, the outer parts of the atmosphere, which are not truly a vacuum, essentially. So we've got that. But we're going to hand wave those away for now. We're going to say, well, there's models that we can use to estimate those, and I really don't want to focus on that at the moment. I want to focus on a relatively simple problem, which is very similar to the toy problem from earlier. It's the observer's position minus the transmitter's position. The norm of that plus some bias is our pseudo range, essentially. And what we'll see is that it's pretty darn difficult to put together an estimation scheme to find your position given, this is your initial problem. So that's where we ended last time. Oops, hang on, I'd like to erase instead. That's where we ended last time. So today we're going to start with this equation, and then we're going to show 2 ways of solving it. And those are both methods of trilateration, lateral as in we have side lengths, right? Triangulation is when you have 3 angles. And so that's a different math problem, which we'll get to at about the halfway point. So there's our introduction. So let's start taking some notes. So previously on Lost in Space, we set up the GPS trilateration problem. Trilateration problem. And so that's going to look like what? So let's say we've got some coordinate system, and I'd like a nice blue color here. So this is going to be the Earth. GPS works on the Earth. It also works in space, kind of. Your mileage may vary. Let's say we've got an observer right here, and let's say that that observer is at some position R sub R for receiver, but then there's also a spacecraft, not my best spacecraft I've ever drawn, and the spacecraft is at some position R sub T for transmitter. So it's transmitting these radio waves. So do some waves, right? And this distance is rho sub I, but we don't know rho sub I. We have a noisy pseudo range. So we're going to say rho sub I squiggle is equal to the norm of the difference in positions. All right, that's my brain going off, sorry. R sub R and R sub T, and it's really R sub Ti because there's going to be multiple transmitters, right? GPS does not work with a single measurement, plus some bias. And so this is the actual range, which is the good part. This is receiver clock bias. And this is a noisy pseudo range. Okay. So let's set this up. We seek a way to estimate R sub R, your position, you the observer's position, given many pseudo range measurements. And let's kind of sharpen the pencil on many. How many do we need? What's the minimum number of GPS measurements that we need to get a unique solution? Somebody remember? We did talk about it last time, or we can just kind of think it through.
I need 4.
4, very good. A lot of people would say 3, because if you have your 3 distances, you can kind of, well, that's trilaterate sounds like 3 distances, right? But actually, at least in the 2D case, we give this great example of if you know that you're some distance away from this point and you're also some distance away from this point, that gives you a Venn diagram with 2 possible solutions for where you are, here or here, right? And so what you really need is some third point to kind of disambiguate, go, oh, wait a minute, it's definitely that one, right? And the same thing happens in 3 dimensions. So in 3 dimensions, 3 range estimates will actually give you, I think it's 4. So I'm trying to remember the intersection of spheres problem, but the point is that there remains some ambiguity, and so we ultimately need a 4th measurement. If you have more than 4, that's fantastic, but yeah, 4 is kind of the minimum for a unique one. Now, what we'll also find is this is not a linear estimation problem. Now, if we go back to last lecture, we went through kind of a toy problem, like a warm-up problem, where we started with this equation. Rho is just equal to your position minus the transmitter's position, take the norm. And then after not that many lines of math, we had a linear system of equations that looked like y equals hx that we could solve. And we're as a class, we're starting to get pretty good at that, going from, the physics model to the estimation theory measurement model, right? And by simply adding a b, that's all we did. Now it looks like this. It's completely unsolvable using least squares, weighted least squares, or maximum likelihood estimation. Those are all out. We are now going to do some other things that we haven't learned how to do yet. This is not a linear estimation problem. Therefore, least squares, weighted least squares, and MLE are out. So what can we do? Ordinarily, I would say, well, why don't we just open this up to, people can think it through. But now what we're going to see today is pretty not intuitive. There's a couple of ways we could maybe think about trying to solve this. But the first is called nonlinear least squares, which sounds like the most simple answer for I have a least squares problem. and it's nonlinear, why don't we use nonlinear least squares? So this is the basic MO. This is what we're after here. We're going to linearize about an initial guess of our state. Then apply the concepts of maximum likelihood estimation once it's been linearized. Then we will update our state estimate and linearize again, and then apply MLE again, and then update again, and basically repeat until convergence. So linearize, MLE, update, repeat, and do this again and again and again until you basically start getting the same answer over and over and over again. So we then need to talk about, well, how do we linearize? And then how do we update? So we'll start with that. So let's say that we start with a state, which looks like this. X is equal to R sub R and B. So, pardon me, this is a 4×1 state vector. Now we'll notice that B, it's not really what we're here for, but it just kind of tags along. So it is okay to estimate things other than position, velocity, and attitude. And oftentimes it's necessary to, just because that's the way the cookie crumbles, right? We really need to include this in our state in order to be able to solve the problem. Y, which is a vector of noisy measurements, is going to be all of our stacked pseudo-range measurements. Okay. And this is going to be an n/1. So then, how do we linearize? How to linearize about some initial guess, which we're going to call X estimated. All right. So whenever we linearize, we got our friend Taylor that we're going to talk to. So if Y is equal to some nonlinear function, which we're going to use the lowercase x, Y is some nonlinear function of X, which looks like this, by the way, right? R minus R, norm plus B, that's this. Well, then, if that's the case, then Y is equal to Y estimated, which is Y of X estimated. So maybe we'll do, yeah, actually, let's just jump right to this. It's Y is Y estimated, which is really H of X estimated plus the derivative of H with respect to X evaluated at X is equal to X estimated. All of that times delta X plus some higher order terms, right? It's kind of dot, dot, dot. There's going to be higher order terms after that. And so, all right, let's clean this up a little bit. That means that delta Y, there we go, delta Y is equal to, essentially, it's going to look like this, dH dx delta x. All right. And so this dH dx, we're just going to call that h. So now h is found by taking a derivative. It's going to be a matrix vector calculus problem. But ultimately, this means that not our state, but the delta in x, the change in our state, can be mapped to the change in our measurements by this h, which is found by linearizing. And this allows us, because remember, we're not really necessarily estimating our state directly. We're starting with an initial guess of our state. So what we really want is, how are we going to update our state? So we end up with a problem that looks like this. So before we move on, it's time for some partial derivatives. Time for some partial derivatives. This is when I love to get audience participation here. So we've got rho I is equal to the norm of RR minus RTI plus B. And if I write this out, it's the same as this, right? It's R sub R minus R sub TI transpose R sub R minus R sub TI, and then close to the 1/2 power plus B. So all I'm doing is just writing out R minus R norm. I'd rather write it out this way because the norm is a weird operator. I'd rather it just be the square root of the sum of the square of the elements, essentially, which is what we're accomplishing here anyway. So now, given that this is our measurement model, we'll start with an easy one so somebody can look really smart for not a lot of effort, which I love doing that. What is the derivative of rho with respect to B?
That's just going to be 1, right?
Just going to be 1. Very good. Excellent. All right. So that's the easy one. So now somebody less fortunate gets to do what is the derivative of rho with respect to R sub R? Oh, crap. All right. Well, let's give it a minute. If anybody is feeling really creative, want to try this one, or I can walk us through it, but I want to see how far people can get. And you don't necessarily need to key in your mic with the full answer. You can just say what we would kind of generally how we would tackle this. All right, a lot of scratching heads. That's fine. So let's think about essentially the way we would solve this is by doing the chain rule, essentially. So what we would end up with is something like this. The derivative of r minus r transpose r minus r to the 1/2 power plus b, well, that is 1/2 r minus r ti transpose r minus r ti. Now the exponent is subtracted by 1, so this is the negative 1/2 power. Okay. And then we take the derivative of the interior. So the derivative of the interior with respect to r sub r would be 2 r sub r minus r sub ti transpose. That's the idea. So it's essentially just the chain rule, right? You take the exponent, comes out front, leave the interior, drop the exponent by 1, then you take the derivative of the interior. And this is the same as, we want to clean this up a little bit, the 2 and the 1/2 cancel out, and all of this is just 1 over the norm that we're used to seeing. So it's really a little bit cleaner. It's r sub r minus r sub ti quantity transpose over r sub r minus r sub ti quantity norm. That's the derivative. So that's some of that matrix vector calculus coming back. And if we know the derivative of both of those, we can say, okay, well, h is the derivative of rho sub I with respect to r sub r, and then it's the derivative of rho sub I with respect to b. There we go. We should think about that for a second. It's going to need to be a 1/4, which should be a little bit obvious, right? So we've got a 4/1, and then this would need to be a 1/4 in order for this to be a scalar, which is a 1/1, right? So just a quick sanity check there. It's a 1/4. Sounds good. And so, I'm going to call this HI, actually. I think I'd rather do that. And so if that's HI, then we could stack several of these together to get something like this. We're going to say delta y1 all the way to delta yn is equal to h1 all the way to hn. I just can't draw equal signs today. Times delta x. And I'll try it one more time with that equal sign. So we would do this for each measurement. That's the point I'm trying to get across, right? Do this for each measurement. We could ultimately build a larger matrix, which is the H matrix. And finally, so this is why it's the nonlinear least squares. We bent ourselves into a pretzel, linearizing about the initial state to ultimately arrive back at a y equals hx problem. And so this kind of lends itself to an iterative solution scheme, iterative solution method. Apologies, I'm just organizing my papers here. This leads to the following iterative method. Okay. Number one, assume some initial guess for your state. And all zeros will do, actually. So this is so iterative methods are notorious for not converging. So we want to be careful about that. Yeah, iterative methods, whenever we do stuff like this, there's a chance that you just spiral off or that it converges to a local minimum but not a global minimum. This particular algorithm is actually pretty darn robust. So you could start with, I think my position and my bias are all zeros, just a 4x1 of zeros. And then it'll actually still converge usually in a relatively short number of iterations. So in this case, we can get away with it. Number two, compute HI for each measurement stack to get H. Okay. Then we compute expected measurement. Kind of glossed over this a little bit because I'm relating delta y to delta x. Well, what is delta y exactly? So we're going to compute the expected measurement. And this is the measurement if we were right about our state. And we know that we're not because we're starting with some initial guess. So if we were right, rho I estimated is equal to R estimated minus R sub TI plus YI is just rho I actual measurement minus rho I estimated. That's what we're getting at. So your delta measurement is the error between the measurement that you really saw and the measurement that you think you should see if you were right about your state. That's the idea. And that allows us to create this stack of measurements, which we'll call this whole thing here. We'll call this delta y vector, and we'll call this whole thing H. Okay. So now we can estimate our state update, not the state, but the state update with MLE. And so as a reminder, this would look like delta X is equal to H transpose R inverse H transpose R inverse delta Y. And then we can update. So estimate the state update with MLE. And then step 5 is update state, which would just be this. X new is equal to X old plus delta X. And if you're coding this up, you can just add in a little check and just say essentially stop once your update, we'll just call it the norm of delta x, is sufficiently small. And in practical cases, we'll say that that's basically less than 1 meter. So when you're updating your state by less than a meter, you can say, all right, we basically know where we are at this point. Then we can say we have converged. And there we are. So that is nonlinear least squares. That is a method of solving not only this, nonlinear estimation problem, but it's actually pretty good for other nonlinear estimation problems. Although you want to be careful about iterative methods in general. They require an initial guess. Where's that initial guess going to come from? They can be sensitive to noise. They can have, difficulty converging. Sometimes they diverge. It can be a bit of a mess. So personally speaking, I would rather have an analytic solution to the problem if one exists. But if there isn't, then kind of a guess and check numerical solution type of thing is on the table. And that's what we have here. So questions about nonlinear least you can use nonlinear least squares or the other one I'm about to show you. All right, so here comes the other method. It's named after Bancroft. I have no idea what Bancroft's first name is.
Actually, can you scroll up to like the top where you started the nonlinear least squares?
Want me to just kind of squat here for a little bit?
It should be good, I think.
Okay. All right, cool. So as I was alluding to, this is a nonlinear iterative solution, which is fine. I would really like it if there was some sort of analytical solution, and maybe one that took up a whole bunch of math and made us look really smart while we were doing it. So this is Bancroft's method. So we're going to start with rho I noisy. So there's our pseudo range measurement is r sub r minus r sub ti plus b. Okay, I'm going to subtract b. So I'm going to say, okay, well, this is really rho sub I minus b, and I'm going to square both sides. That allows us to unpack this and say, well, this is really r sub r minus r sub ti squared. And if we distribute to both sides, what's this going to be? So this goes back to our high school math or maybe middle school math foiling, right? This is going to be rho sub I squared minus 2 rho sub I b plus b squared is equal to, so this is just the r sub r minus r sub ti transpose r sub r minus r sub ti, and then we don't take the square root because it cancels out. So that would be what? It would be r sub r transpose r sub r minus 2 r sub ti transpose r sub r plus r sub ti transpose r sub ti. All right, that's just foiling. We're just distributing what's on both sides of the equation there. Foiling standing for first, outer, inner, last. I'm not sure if everybody learned it that way, but that's the binomial times binomial distribution method. That's how I learned it. So we're going to group some terms. All right, so bear with me. All I'm doing is just changing on who's on what side of the equal sign. So on the left-hand side, I'm going to call this r sub ti transpose r sub r minus rho I b. And that's equal to 1/2. You'll notice I've divided everybody by a half now. 1/2 r sub r transpose r sub r minus b squared plus 1/2 r sub ti transpose r sub ti minus rho I squared. Okay, and that should have a squiggle. There we go. All right, so all I did was divide by 2 and then move around who's on what side of the equal sign. Okay, why did I do that? All right, the reason is that the right-hand side of the equal sign can be grouped into a couple of terms. I'm going to take this whole term And what do we notice about it? Those are all of the things that depend on the state and don't change from station to station or from measurement to measurement, right? Nothing in this term has anything to do with the particular GPS satellite that we're looking at. It's just a function of the state. I'm going to call this lambda, and it is a function of the state only. And then this whole second term, you'll notice, has nothing to do with the state and everything to do with the particular GPS spacecraft that we're dealing with. So I'm going to call this C sub I, which is a function of the measurement, essentially, or information. We're assuming that we know the position of the spacecraft, but essentially, this has nothing to do with state. This is independent of state. All right, so we've got all this on the right-hand side. On the left-hand side, we've got R sub Ti transpose R sub R minus rho I B. Okay, so in this case, what I'm going to do, so what we'll see in a second here is that this can be written in a linear-ish set of equations for R sub R and B. So bear with me for 1 second. I'm going to define two things. So first, we will define two things. First, as in the last solution method, X is R sub R followed by B, which is a 4/1. And then I'm going to introduce a new matrix, which we're going to call beta, which is just the identity matrix, only with a negative final element. So 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, negative 1. Okay. That's what beta is. The reason is we've got this minus sign here that's kind of annoying. So we're going to introduce the beta matrix. So what this allows us to do, and this is going to be the biggest single jump in the entire Bancroft method, is to say this. Right? R T1 transpose rho 1 all the way down to R, I don't know why I just said R and then wrote rho. It's not what I was trying to do. R sub Tn transpose rho n. So what you'll notice is all we did was take the left-hand side and we just group it so that we have, this matrix multiplying our state, X. But it doesn't quite work out that way because we've got this nasty minus sign, so we're going to throw beta in the middle. So really what we're saying is this whole matrix times beta times X is equal to lambda, which is a function of our state. So it does not change from measurement to measurement. So I'm going to factor it out. It's really lambda, 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 lambda. I'm going to say as lambda, and then within the matrix, it's just a matrix of ones. Right? Lambda followed by a matrix of ones plus, and then we have all of the C's, C1 all the way to Cn. Okay. So we're taking our measurements, we're kind of rewriting a few things. Lambda is some function of the state, and Ci is independent of the state. Beta is defined over here. And so we have this matrix, which I'm going to call A. We have this matrix of just ones, which I'm going to call L. And we have this matrix of just C's, which I'm going to call C without a subscript, meaning that's the whole thing. Okay. So we did a lot of definitions. We defined some things as lambda. We defined some things as C. The reason we did that is so that we can now write a much cleaner equation, which looks like this. A beta state is equal to lambda L plus C. All right. So you might be thinking to yourself, how the heck does that buy us anything? It's like, well, bear with me for a second. Hopefully it makes sense how we got here. We did some definitions and we've defined A, we've defined lambda, we've defined C. What we notice is that the state kind of appears twice in here, right? Because the state is rolled up in that lambda, and it's also explicit in there's the X on the left-hand side. And so here's what I'd like to do. I'm going to do a few more steps to try to clean this up even further. So continue to bear with me. What I would say is, why don't we just do this? Beta x is equal to, remember, A is not guaranteed to be an invertible matrix. So we're going to take the pseudo inverse, which is the same as just a least squares solution. So this is going to be A transpose A inverse A transpose, and then in parentheses, lambda L plus C. Okay. So we have beta x is equal to A transpose A inverse A transpose lambda L plus C. Okay. I'm going to define all of this, A transpose A inverse A transpose, as B. So this is kind of the thing about the Bancroft methods. They keep saying, no, after 3 more steps, we're going to call this other thing, just to keep the equations looking kind of pretty. So now we have beta x is equal to B. I'm going to distribute. So it's going to be lambda BL plus BC. And you're never going to believe what's going to happen next. We're going to redefine some things. BL is going to be called U. And U is a vector. And then BC is going to be called V, where V is a vector. So now we've arrived at the equation beta times the state is equal to lambda U plus V. You might be feeling a little bit lost, but remember that U and V are determined by B and L and C. B is some function of the matrix A, and we know what the matrix A is. It's built out of actually things that we know. It's built out of measurements and positions of spacecraft. So A, everything in A is known. L is just a bunch of ones. C is just some function of, also things that we know. So the positions of the spacecraft and the ranges. So we now have a slightly cleaner equation where, again, we have the state appearing on the left and the right. It would be really nice if we knew lambda. If we knew lambda, this would all be a lot easier. Now, there's a few tricks that we're going to trot out in a second here. So first, here's one of our tricks. Observe that if we said beta times x quantity transpose times beta x is the same thing as x transpose beta x, and that's the same thing as lambda U plus V transpose beta lambda U plus V. All right, doesn't feel like that helps us a lot, but that's just a true statement based on the matrix vector map that we have in front of us. So x transpose beta x is equal to this stuff if we just distribute. Now we can also observe, and this is where our definition of lambda is going to help us here actually, and of our state. Also observe that x transpose beta x, well, x is, if we just scroll up for a little bit, x is our position and then the bias. So the position transpose, so this whole state transposed with itself, and then with the beta in there, which changes one of the signs, that's just going to be r sub r transpose r sub r minus b squared. But that's exactly the same thing as 2 lambda, right? When we originally defined what lambda was all the way up here, it's r sub r transpose r sub r minus b squared. So we found a way to turn the state into lambda again. Finally, what we're going to see in a second here is we're ultimately allowed to eliminate this x, and we're going to have an equation in terms of lambda. So if we know that x transpose beta x is equal to 2 lambda, but x transpose beta x is also equal to all this stuff on the right-hand side, and we combine this information, that gives us that 2 lambda is equal to lambda U plus V transpose beta lambda U plus V, where again, we know everything in U, we know everything in V, and we know beta. we're just looking for lambda. So let's clean this up a little bit. 2 lambda, if we distribute, would be equal to lambda squared u transpose beta u. That's the first term, so first times the first. And then the outer and inner is going to be plus 2, and we'll just focus on the u being on the left. So it's going to be 2 lambda u transpose beta v. And then we've got v transpose beta v is our third term. Okay. Now, remembering that this is actually, we'll put this up here. This may or may not be obvious, but beta inverse is just the same as beta. So we're going to get a little bit sloppy about our inverses in a second, but we can get away with it. We can turn this into a polynomial, which looks like this. Lambda squared times u transpose beta u plus 2 lambda, and then in parentheses, u transpose beta v minus 1. So that's, we're moving this 2 lambda over to the other side of the equal sign. Plus v transpose beta v is all equal to 0. All right. So this might seem like we've reached a completely arbitrary step and I have no idea what Paul's going to do next. But I'm saying, no, this is it. The train has arrived at the station. We're done. Might not be obvious why yet. This is a quadratic polynomial in lambda where lambda is the only unknown. So we've done all of this fancy math, all this matrix vector stuff to ultimately arrive at a high school math problem, which is trying to find the roots of a parabola. That's where we are now. So we've got lambda squared times some stuff plus 2 lambda times some stuff plus some stuff equals 0. We know all of these coefficients. And so the strategy is this. Here's the strategy. Is set up the quadratic polynomial which might seem impossible, but it's just made out of u and beta and v. And u and beta and v are all built out of things that we know. So it's, you know, it would be a lot to try to do this by hand, but you can do this in the calculator or in MATLAB pretty quickly. Set up this polynomial, solve for lambda, and then we can find our state. And remember that our state is just beta times lambda u plus v. And so there we go. So we've got our state, which is our position and our bias, after we solve this quadratic polynomial in lambda. And none of this was iterative, and this is all analytical. This is going to run faster and fewer computations than nonlinear least squares. Problem is, again, we come back to this initial guess situation. Whenever you've got an iterative solver, you know that you need an initial guess. Whenever you've got a polynomial, you know that there are going to be multiple roots, right? In general, a polynomial quadratic is going to have 2 roots. And so how are we going to handle that? So there will be, in general, in general, 2 solutions for lambda. However, only one produces a state consistent with pseudo ranges. The other one is going to be a mathematical oddity. So essentially, you would just go through and try both. So try both and see what works. And that's the procedure. So as ugly as it might have been, ultimately we have the A matrix, the L matrix, and the C matrix, which are built out of things that we know and understand. Those ultimately turn into the U vector and the V vector, which become these coefficients of this polynomial, which is quadratic in lambda. We solve for lambda, we find the state, bing, bang, boom, you're done. all of this is about 10 lines in MATLAB or Python, and then you're good to go. I ultimately decided to use the Bancroft method rather than nonlinear least squares, but whichever one of these feels more intuitive to you, you're welcome to use. But yeah, either of those would allow you to do homework 3, problem 1, which just as a review, homework 3, problem 1, you're given 5 GPS satellites and you're given their orbit elements rather than their position. So you're going to have to use the math that you used in homework 1 to find the actual position of these different spacecraft at the time, 3 hours since the start of the sidereal day. We get these pseudo-range measurements, and so you've been tasked to use either nonlinear least squares or Bancroft's method to perform trilateration and find the position of the observer at t equals 3 hours. I would like to know this in terms of latitude, longitude. So I don't want to know the position in terms of x, y, z in the Earth-centered inertial frame. I want to know where the person is on the surface of the Earth. And actually, if I've done this right, this should be like a recognizable location on the surface of the Earth. So I'd like to know where that is, which is just as simple as typing in the coordinates to Google Maps, essentially. Hint, just to make sure we don't mess this up, you will need to propagate the states of the GPS satellite forward in time, right? All of this information I've given you are their orbit elements describing their position at time 0. I'm asking for 3 hours later. So each of these needs to be propagated forward 3 hours. And also, when you find the observer position, you're going to find it in the same frame as the frame that the spacecraft are defined in, which is the Earth-centered inertial frame. So at some point, you're going to need to think about converting from Earth-centered inertial back to ECEF. So I kind of had to tack on the orbit propagation and ECI to ECEF problems. Otherwise, this would be way too easy, because essentially we're just taking 5 pseudo-range measurements using nonlinear least squares or Bancroft, and ultimately finding the location of the observer. So hopefully this doesn't pose too much of a challenge. Certainly, if you get stuck on it, I'll be able to answer questions in office hours or after class on Thursday. I'm going to try to pay closer attention to my email this week. But anyway, that is our discussion on trilateration, and that is hopefully everything that you need to thrive on homework 3, problem 1. So I think that's a good spot to take a break. And then in 5 minutes, when we come back, we can talk about triangulation. But I'll stick around to answer any questions that y'all might have during the break. Otherwise, let's meet back here at 7:11.
Well, I had a question about what you're talking about earlier with homework 2 and finding the state at T0 versus TF and then propagating forwards.
Yes, yeah, the stuff we talked about before the lecture started. Yeah, what were you thinking about?
So I was one of the people that solved it at T0 and then propagated forwards,
Yeah.
thinking that if we then wanted to find it at some other time, we could then just go back to the system that we already had and just plug in a new time. Is
Mhm.
there any merit to that, or is that just total nonsense?
I mean, no, so I definitely I didn't take any points off of anybody who did the initial estimate and then propagate, because that is a valid way of doing it. Because ultimately, what the state transition matrix allows you to do is perform that propagation in the form of matrix math rather than in the form of scalar math. So I don't think that there was anything wrong with what you did. I don't remember if I've graded yours yet, but if I did not take points off for doing that. Now, the trap that people will fall into is that the state covariance, P, will be estimated at the initial time, and that absolutely does change over time. That's, and it's not obvious to me how best we would propagate that. So folks who found the state at the initial time and then propagated did not get points off, but you do need to use the state transition matrix to find the right P value.
Okay, so it's just the other part of my question. If we if we then wanted to say find the state at t equals 30 or t equals 40,
Mhm.
is it computationally the same to just redo the batch estimation with a different time in the matrix?
Yep, that'd be fine. Just pop in a different time. You can make the time a variable, so you can just set it upstream of your, somewhere else in your code, and then just change that number, and then you're good to go. So yeah, I definitely prefer to do it that way rather than the propagate, mostly just because that makes it easier when the time comes to find your covariance as well. But what I was worried was, I think that, and maybe this wasn't you, but I was worried that people were not exactly pattern matching, but they were a little bit too timid about doing something different than what I did in lecture. They kind of just took what we did in lecture and then applied that to the homework, which isn't wrong. Sorry, it isn't wrong, but it's just not quite what I wanted. So yeah, like I said, I didn't take points off, but I wanted to be very abundantly clear about, this is also an option. I want it to be in your awareness.
Got it. Thank you.
Yep. All right, I figure that's a good time to start back up. So we'll ease into our next discussion. There we are. So there's a couple of different ways. We've talked about two ways of solving trilateration. Now we're going to talk about two ways of solving triangulation. Really, we're going to nod to four ways of solving it, but we're really going to lean on two ways of solving it. So triangulation. And now for something completely different. Using angles instead of ranges. So for pretty much all of last class and a lot of this class, we talked about this problem of, okay, well, I know my distance away from these four satellites. Now what I'm saying is I've got either line of sight measurement to 4 points on the surface or 4 observers on the surface all taking simultaneous line of sight measurements to something in space. So it works either way. We're going to set the problem up like this. Let's say that you've got your reference frame. And let's say that you've got a spacecraft with a little camera on it. And it's at some position R. And let's say, oh, I wonder if my microphone's going to pick that up. Was that complete silence or was there like a booming noise in the background?
It was silent.
Oh, well, that's disappointing. I'm sorry. We had a couple of astronauts just flying by overhead on T-38s, and they were really low and fast, and it sounded pretty cool. And I was like, oh, be great if that came on the microphone. But all right, that's fine. That's one of the cool things about living next to Johnson Space Center. You get the astronauts flying by overhead, pretty loud. If I wasn't a space geek, I'd probably get tired of that real fast. But like, I am a space geek, so it's awesome. So we've got some point on the surface, and we could think of this as a point that's been placed here, like an observation station, or it could be the vector to just some crater on the surface of the moon or some landmark on the surface of Mars. But we've got 2 points here, and then let's say that we've got line of sights, where in this case, we've got a vector that looks like this. I'm going to call this one U1, call this one U2. So our equation looks like this. The position of the spacecraft plus some unknown range. Yep, there's the range again. So rho I UI, where this is the line of sight direction from the spacecraft to the point on the surface, is equal to the point on the surface. This is going to look a little bit like the observation equation for Gauss's method of angles only orbit determination, because this is an angles only method of position determination. And actually, for those of you that are familiar with the perspective endpoint problem, triangulation is kind of a baby version of the perspective endpoint problem. Perspective endpoint is when you have an image of multiple points and you know where those points are in real life and you know where they are in the image, and you're trying to find your position and your attitude at the same time. In this case, we're saying that the entire problem is done in the same reference frame, which means you know your spacecraft's attitude, you're just trying to find its position. So this is an easier problem. So let me ask this question. We know that we need 4 measurements when we're doing trilateration. How many measurements do we need when we're doing triangulation?
You just need 3, right?
Ah, so what's your logic behind 3, Corey?
Um, if you have 3 lines pointing out into space, they're going to be closest to each other at 1 point and 1 point only.
Okay, so you're right that 3 would do it, but could we get away with even fewer?
Oh, you could do it with 2.
Could we do it with just 1?
No.
Okay. You're absolutely right that it's 2 is kind of the line. So there's the way where you just kind of stop and think about it and do a geometry problem in your head, which is perfectly valid. I like to use the degrees of freedom kind of technique, right? So we know that our position has 3 degrees of freedom, right? X, Y, and Z. Each measurement, UI, has how many degrees of freedom are there in a unit vector? You're not off the hook, Corey. I hope you didn't turn your microphone off. Come on, come on.
Sorry, 2.
It's 2. Okay, very good. 2 degrees of freedom. It's tempting to say 3 because it's a 3 by 1 vector, but remember it's unity norm. So you could think of it as if you're an observer standing on the surface and you're looking at the moon, and this way is north, and the moon is up here, then it's going to be like this, right? You've got your angle from north. So that's your azimuth direction, and then you've got your elevation direction. So as and L, those are your 2 degrees of freedom. Or you could think of it, there's a couple of ways you could conceive of it, but directions in general are 2 degrees of freedom, not 3 degrees of freedom. And so you can think about it. Okay, 1 direction is absolutely not enough because 2 is less than 3. 2 directions is actually even more than we need because that would give us 4. But there's no way to have a direction and a half. So in this case, it is going to be 2 measurements. So each of 2 degrees of freedom, you can think of those as an L. So therefore, we need 2 or more measurements. All right, nice work, Corey. That's supposed to be an M. I'm just having a hard time today. All right, there we go. Let's see. So how do we solve it? There's two methods we're going to talk about today. One of them is called explicit range estimation. That's how we're going to start off. Now, I'm going to be very clear that I'm biased and I have my favorites, and my favorite is not this, but this is a perfectly valid way of solving the problem. So this is explicit range estimation. All right. So how do we do this? Well, we're going to start with the problem, just like we have written up above. R plus rho I ui is equal to pi. And so there's basically two ways to solve this. Well, there's the way we're going to talk about now, there's the way we're going to talk about in a second. One of these is to try desperately to rework this to get rid of R, so the only unknown is the range. And once you know the ranges, you're good to go. The other is to try desperately to get rid of the range, so the only unknown is R. First, we're going to solve for the range, explicit range estimation. So you can think of it this way, right? R is equal to pi minus rho I ui, but it's also equal to pj. I don't know why I put a little hat on that. There we go, sorry. Pj minus rho j uj, right? Those are equally true. Okay, but that means that we can just ignore R altogether, and we could say, okay, then, after a little bit of rearranging, rho I ui minus rho j uj is equal to pi minus pj. So observer position R has been removed. Not part of the problem anymore. Okay, great. Can we turn this into a linear system of equations to solve for rho I and rho j? You bet we can. That's what's going to happen next. So first, I'm going to rework this by, we're going to basically left multiply, how do I want to do this here? Oh, I see. Okay, sorry. I was confused by my own notes. We're going to right multiply everything by u sub I. So just bear with me for a second, right? It's going to look like this. Rho I ui transpose ui minus rho j uj transpose ui, hopefully you see the pattern now, is equal to pi, keep putting a little hat on it, pi transpose ui minus pj transpose ui, right? And so what that gives us is that rho I transpose rho I, or I keep saying rho, sorry, only listen to me when I'm right. I'm getting tired and I'm starting to make mistakes here. Rho, this is times 1, right? Any unit vector transposed with itself is just 1. So we ultimately get rho I minus rho j uj transpose ui is equal to pi transpose ui minus pj transpose ui. And you can imagine that we could do the exact same thing the other way around to solve for rho sub j, right? So using any two landmarks, we can create a linear system. And that's going to look like this. Might be obvious. The top line is just this equation, right? 1 negative uj transpose ui rho I rho j, and then the right hand side of the equal sign is just going to be ui transpose pi minus pj. And we could play this exact same game if we had focused on rho j. So this would look like ui transpose uj and -1. And then this would be uj transpose pi minus pj. There we are. And so we can solve this using least squares. And then we can just take either range, right? Either one is totally valid. So your position is equal to pi minus rho I ui, but it's equally valid to say that it's pj minus rho j uj. And there we go. So this is a perfectly valid way of solving the problem with a couple of drawbacks. There are a few kind of, just a warning before we move forward with this. So in the absence of measurement noise, this is perfect, which is nice. We would hope so, right? In the absence of noise, this will precisely recover R. Problem is, navigation is not a geometry problem so much as it's an estimation problem. There's always noise, right? This will precisely recover R. If we had absolute knowledge of anything in the entire problem, that would be great, but it's all estimates. In the presence of noise, we'll just say in real life, we would like to use many landmarks. Several as in more than 2 landmarks. So here's the rub, right? This explicit range estimation scales poorly. So I've shown it to you for a system of 2 landmarks. But what happens is a system of 3, well, let me go through an example here. Explicit range estimation scales poorly. So what do I mean by that? If we have 3 ranges, gives 6 equations and 3 unknowns. And more generally, if we have n ranges, November, n ranges gives 2n choose 2, right? So going back to combinations and permutations, 2n choose 2 equations and n unknowns. So the size of this matrix problem is going to start to get huge, and it's going to grow way, way faster than the number of ranges, right? So for example, let's say that we were trying to triangulate using an image of the lunar surface where we had 1,000 landmarks, and it's, well, let's dial it back, let's do 100. It's totally not unreasonable to consider having 100 valid landmarks in an image of another celestial body. That's kind of an extreme case, but it's within the realm of reason. A lunar surface image could contain 100 or more landmarks. Not necessarily craters, but like identifiable feature points that you could use, right? And so this would give a 9,900 by 100 matrix that you would need to solve. So we're not doing that, right? In general, and whenever possible, we prefer linear problems that actually scale linearly. That's what we're after. So explicit range estimation, totally fine if you have 2 measurements. In the homework, you might have guessed, we have a triangulation problem coming up. I gave you 3 measurements. So you could, give it the old college try, although I tend to prefer, and I'm clearly biased, this next method that we're going to talk about, which is called the direct linear transform. But so before we move on, any questions about explicit range estimation? All right. So you might have noticed it's the bottom of the hour. We're not quite done. I've got about 1 page of stuff left, so we're going to run a little bit late. That's my fault. I took a 15-minute head start to do announcements at the beginning, but I hope you'll agree that this is worth our time. We're just going to power through, finish this up in about another 10 or 15 minutes, let you go, and then you'll have everything you need to do well on homework 3. So the direct linear transform is essentially just the vector form of the law of sines, right? Remember, our problem looks like this. So we've got r plus rho I u I is equal to pi. And before I said, well, we're going to do everything we can to get rid of r so that the problem just becomes about finding the ranges. I'd rather ignore the ranges entirely, and here's a cool way to do that. We're going to take ui crossed with both sides of this equation. So ui crossed r plus rho I ui is equal to ui crossed pi. Okay. Well, then, in this case, this is ui crossed r plus rho I ui crossed ui. But you might remember that any vector crossed with itself is just 0. And hey, look, the range is then zeroed out in this case. Ui crossed pi. You might say, okay, fine, but how in the world are we going to break out r, right? R is what we're trying to estimate, but it's in the middle of a cross product operation. Well, remember that A crossed with B can also be written as A cross times B, where this is the cross product matrix. So we can turn the vector A into the cross product matrix of itself. And we talked about this, oh gosh, I'm not sure which lecture we went over this, but it's pretty early on. I think it was in attitude representations, lecture 4 or 5. We talked about this cross product matrix. Well, it just came back because now what we can do is we can stack a whole bunch of cross product matrices and we get ui, or let's make it u1 all the way to un for however many n are. But these are each cross, right? So they're to the power of the cross product operator, means these are each a 3x3 cross product matrix. Let me scroll down a tiny bit here. So this is going to be a 3n by 3 matrix. And all of this times r is equal to u1 crossed p1 all the way to un crossed en, which is going to be a 3n crossed 1, right? Where r is a 3 by 1. So that all checks out. And we can take this problem and solve for r using least squares. And I have to say, given how powerful the direct linear transform is, this is probably the shortest derivation we're ever going to see in this class. Like, it's just that many lines and you're done. And I vastly prefer this. Not only because it's so simple, but actually it scales in a fantastic way. So you can imagine using this with 100 measurements. It's not going to scale as 2n choose 2. It's going to scale linearly with a number of measurements. In my dissertation and in some of my research, and even some of my work since I've started at NASA, I've been doing the direct linear transform as kind of my go-to triangulation algorithm. Although that we can improve on it. I want to be clear. There are definitely better algorithms out there, and we're going to talk about one of them right now. So the direct linear transform, DLT, is simple. In my opinion, it's beautiful, and it scales well. But we can do better. I know that y'all have been missing my art skills, so here we go. This is me trying to do some kind of trying to get the idea across here. So we're going to consider 3 different cases. Let's say that this is the moon, right? And here's your spacecraft with a little camera on it, right? And let's say that you've got some feature up here, could be a crater, could be something else. You've got some feature over here, could be a crater, something else. You've got some feature over here, could be a crater, could be something else. And you're using these 3 to triangulate your position. Well, if you have no noise, it's a perfect problem, but you do have noise, right? So you could think of it this way. You've got a little bit of uncertainty in your direction, in your line of sight direction to each one of these craters. You could think of it as saying, this crater says, oh, you know, the observer, he's that way. And the other one goes, no, the observer's that way. And the observer's that way. The intersection of those 3 lines is a point. But really, it's better to think of it as a cone. So your uncertainty in the first measurement produces some cone saying, well, I think that that feature is that way, but I'm not quite so sure. And my uncertainty produces this cone. So I really know I'm somewhere in the cone, not necessarily along the line. And then the same thing happens with the second measurement. I'm really somewhere in the cone. I'm going to try a little bit harder to draw a cone. Just bear with me here. I'm really somewhere in the cone, not, ooh, that's even worse. 3rd time's the charm. There we go. I'm really somewhere in the cone, not somewhere on the line. That's as good as that's going to get. And then similarly up here, right? I'm really somewhere in the cone, not somewhere on the line. And so what you end up with is this estimation of the intersection of 3 cones problem, or kind of looks like 3 spotlights all shining on an aircraft. But you've got this estimation of 3 cones, and your bearing error means that you really are inside of some blob, and that blob is going to be your covariance, right? So you've got this bearing error causes it to be a cone. That blob is your covariance. So you'd imagine that you'd have a larger covariance if you had a larger bearing error. That's all well and good. Now let's consider the problem where it's the same moon, hasn't moved. You've got feature point here, feature point here, feature point here, and you've got a spacecraft all the way down here. Okay. What's the problem now? Well, so you've got your, I see one this way, and I see one this way, and I see one this way, and it's the same bearing error. So it's going to be the same cone angle for each of these, right? But what ends up happening is, because some of them are further away, that same cone angle propagates to a larger uncertainty. So in this case, because this landmark is much, much further away than the others, the cone, it's the same angle, but it just, because of the distance, you've got a greater uncertainty. So I want to be clear, the same bearing error for each measurement, but not the same uncertainty for each measurement. Clearly, we want to favor nearby measurements. And we can think of an even more extreme case, right? What if instead of using craters and you're over the moon and you're looking at an oblique angle, what if you are in interplanetary space, and this is part of my dissertation, and let's say that you are looking at, here's a spacecraft, and let's say that you know that this is the Earth, and let's say that over here we've got Saturn. This is totally not to scale. You're trying to perform triangulation at distances, at you know, celestial distances, essentially. Well, it's going to be the same idea. There's going to be a relatively narrow cone from Earth, and then an absolutely humongous cone coming from Saturn, because Saturn is just so much further away. So this is an even more extreme example. So what does this motivate? You might have already guessed the punchline here. We want to solve a least squares problem where some measurements are more trustworthy than others. That sounds an awful lot like weighted least squares. So we have a weighted form of the direct linear transform. And I like to mention this. This is my favorite. I think I asked for this explicitly in homework 3. And this was also developed at RPI, which you might think is kind of cool. So how do we do this? To account for our range dependent error, we just weight each measurement. That's basically what it comes down to. So to account for range dependent error, we weight WIGHT each measurement by what else? How about 1 over the range squared? Sounds good to me. So this results in a diagonal weighting matrix which is going to look like W is equal to, actually, I should be clear, it is a block diagonal weighting matrix. So it's going to be identity, but then another identity, and then another identity. It's really going to look like, oh, you know what? I take it back. This will be a regular diagonal. I guess regular diagonal is a subset of block diagonal. It's going to be 1 over rho 1 squared times I 3 by 3, zeros, zeros, and then 1 over rho n squared times I 3 by 3. So you get this block diagonal weighting matrix. And then we know that R is equal to H transpose W H inverse H transpose W Y, right? That's how we solve a weighted least squares problem. Now, some of y'all might be getting ready to yell at me because, wait a minute, Paul, we are trying to use the ranges to weight this least squares problem, but we don't know the ranges. That's the whole point. The whole point of the direct linear transform is that we don't know what the ranges are. Yes, I'm aware of that. The procedure is essentially to solve the regular least squares form of direct linear transform. You'll get a range estimate, you'll get a state estimate. You know that it will be slightly wrong. There's going to be some uncertainties, but you could then use the ranges that you compute to form W and then do this in an iterative sense. And just like the iterative least squares that we saw earlier, this is a pretty robust iteration scheme, and it usually converges within very few steps. So I'm a big fan of this. And let's see here. Yes. Observe that the weights require us to know the ranges. This seems backwards. So here's the procedure. Number 1, set up and solve the regular unweighted least squares version of the DLT, direct linear transform problem. Then use your estimated position to compute estimated ranges. So we'll call these rho I, where I equals 1 to n. Then build your weighting matrix W. And then we're going to solve weighted direct linear transform problem, which is basically the weighted least squares problem. And then finally, just repeat steps 2 through 4 until convergence, which is usually quite rapid. All right. So then y'all might be thinking, and rest assured, we're very almost done. We're certainly within 5 minutes of being done. You might be thinking, okay, Paul, so we talked about the direct linear transform, which is ultimately a least squares problem. And then we talked about the weighted direct linear transform, which is an improvement on that, and which is like a weighted least squares problem. I remember from estimation theory that there's something even cooler than weighted least squares called maximum likelihood estimation. There must be a maximum likelihood estimation equivalent to the direct linear transform, and there is. And we are not going to cover it in this class, partially because you already have the tools that you need to survive and thrive on this homework, partially because this is a little bit more fancy and it is better. It does outperform the other methods, but I think that direct linear transform is a little bit easier to comprehend. It's a little bit easier to just kind of code up and run. We're going to focus on weighted DLT in this class, but for your awareness, there is an additional algorithm, which we'll just talk about very briefly, called the linear optimal sines triangulation algorithm. Somebody with a sense of humor named it because it spells lost. Linear optimal sines triangulation algorithm. So the natural evolution of DLT and weighted least squares DLT is maximum likelihood estimation DLT. And that's exactly what this is. And this is the lost algorithm. It is more complicated. Takes longer to set up. But as you might expect, it outperforms the DLT and the weighted DLT. This is basically the best. And it is, because it's the maximum likelihood estimation equivalent, there isn't something better. Like maximum likelihood estimation is by definition the best possible estimate for this linear measurement scheme. And so when we have a triangulation problem, lost is pretty much the theoretical best thing we could hope for, right? That's basically it. And so it comes from a paper. And so if you want to read more about it, in fact, this could even be something that you do for your term paper. It's called Absolute Triangulation Algorithms for Space Exploration by Henri and Christian, published in 2022. So triangulation is absolutely still an active area of research. There's always still more work to be done. So we're not going to go into much more detail in this class. So this is just for awareness. We will focus on weighted direct linear transform in this class. There we go. And that's it. That concludes our discussion on triangulation and trilateration. Y'all have everything that you need to survive and thrive on homework 3. So as a reminder, homework 3, problem 2, we have a spacecraft over the moon. We've got 3 craters, and I'm giving you the latitude and longitude of those craters. And there's a bonus question. Do any of these craters have a name? And hint, one of them does. And we say, okay, the spacecraft is in orbit of the moon, and it captures these line of sight measurements in its optical navigation camera frame. And then we also have a quaternion, which will allow you to go from the International Celestial Reference Frame to the Star Tracker frame. And that's presented as a scalar and a vector. We also have a quaternion that allows us to go from the Star Tracker frame to the camera frame. And we know that in order to solve a direct linear transform type problem, we need to be working all in one frame. So y'all will need to do some quaternion math. So that's kind of, I snuck that into this homework assignment. And when you do the quaternion math, ultimately we're trying to build in the direction of having these line of sight directions in the inertial frame, right? And then you've got your crater positions, which you could also find those in the inertial frame. So you need to get your crater positions in the moon-centered inertial frame, measurements in moon-centered inertial. Once it's all in one frame, it's relatively straightforward to set up an iterative weighted direct linear transform problem to estimate the position of the spacecraft. And you're going to do this 3 times. You've got it at 0.3 hours, 0.5 hours, and 0.7 hours. So there's 3 different measurement times, 3 different inertial positions. And now you might already be guessing where we're going to go with this. If you know the position of a spacecraft at one time, and then you know it at another time, and then you know it at a third time, what do? That's called Gibbs method. So we can go all the way from knowing our different measurements, all the way from having these pictures of the surface of the moon and recognizing craters. We can triangulate our position at 3 different times, and then basically draw a thread between them, and that is going to be our orbit by solving Gibbs method. So those of you that attempted Gibbs method on homework 1 are going to have a leg up on this assignment. Quick hint, the craters are going to move between measurements, so you need to be taking that into account. You'll want to do all your work in the inertial frame, so do your best to get into the inertial frame. Be careful of the signs of your direct linear transform equations. And also, I should mention that this homework problem is chapter 3 of Kevin Kabilka's dissertation, who's an RPI student currently working at NASA. We might hear from him at a guest lecture if there's time later this semester. But he's a fellow John Christian PhD student, and this was part of his dissertation. So I'm kind of, I would be plagiarizing if I weren't if I weren't citing it right here. But yeah, so thanks to Dr. Kabilka, and yeah, that's pretty much everything. So y'all should be in a good state to tackle homework 3. Thank you for sticking around. I know we're a little bit later today than we'd usually like to go to, but I hope y'all are able to digest all this and then go tackle homework 3. Let me know if any other questions. Otherwise, we're going to dismiss for today, and I'll stick around for a little bit if y'all want to chat. So thanks, everyone.